I think
Okay,
you
we
can.
can start.
Yeah.
Very good afternoon and welcome all of you to the Silver Jubilee lecture series organized by ISP. Today, it is my privilege to introduce to all of you Professor Dr. Matjaz Valant. Professor Matjaz Valant is the head of the Materials Research Laboratory and Dean of School of Environmental Sciences at the University of Nova Gorica, Slovenia. Professor Valant is also an adjunct professor at Institute of Fundamental and Frontier Sciences, University of Electronic Science and Technology of China, Chengdu. He is also the vice president of the Slovenian Chemical Society. Some of his notable previous appointments include a postdoc position at University of Pennsylvania, USA, a visiting professor at London South Bank University, UK, and a long-term academic visitor at the Imperial College, London. His area of interest includes high-temperature phase relations, phase change materials, hydrogen production by green algae, polycarbosilanes, oxide coatings, grid energy storage, topological insulators, chlorine chemistry, multiferroics, photocatalysts, electrocalorics, etc. We are deeply honored to have him today to give a lecture at the Silver Jubilee Lecture Series. It is our second lecture of the many to come, and the title of today's talk is General Trends in Chemical Interaction of Metals and Bismuth Selenite Topological Insulator. Welcome, Professor Valant, to the International School of Photonics, Busan. Thank you.
Thank you very much for this kind introduction. I would prefer to be there with you and share our work and our results with you live, but unfortunately we have to meet online. Well, I'm optimistic that this will disappear and we can get back to normal soon. Okay, I will start sharing my screen with a little bit of introduction into our laboratory and our activities, and then I move to the topic of the talk, which are topological insulators. Let me now share the screen. Oh,
It works.
it works, great. Okay, so as it has been introduced, the title is General Trends in Chemical Interaction of Metals and Topological Insulators. I will explain the motivation for this work later, but first of all, I would like to show you the map of Europe. This is the map of Europe, quite colorful, and I would like to point out my little country, which is this blue spot in the middle of the Europe. It's very small, you see, and it's just over 2 million of population. And your colleague Praveen has obtained his doctoral thesis from the university which is located in this country. And he left a mark in our laboratories for sure. Okay, so this is our area. It's quite green, a lot of greenery, a lot of outdoor activities, a lot of fruits is growing here. It's actually quite pleasant area and a lot of things to do. This is our group. The picture is a little bit older, but we are a little bit more people in the group now. But as you can see, we are decently equipped with state-of-the-art microscopy, with a lot of other instrumentation that allows us to do all kinds of research. I would also like to point out that just 30 kilometers away, there is a synchrotron facility, which we are quite often using. And what you're going to see a lot of results for this synchrotron facility, actually just over the border in Italy. Okay, now what we are doing in the lab. So we are doing research from, we are doing research from basic level to industrial R&D. For instance, just down at the basic level, we have a group of theoreticians, actually, which I must say, Praveen has started at that time. And now we have expanded it, and we are doing very, very different kind of modeling. Something also for the fusion reactor ITER. We are modeling materials under extreme environment to see how for instance, electronics will behave under a lot of irradiation damage. And of course, for that reason, we have established a lot of collaboration, especially with France and Italy. Then we go a little bit further up, where actually, I will just move a little bit further up. Sorry, this is a little bit overlap with, and we stop at the topological insulators, and this is actually the topic which I'm gonna return later and talk about that. Okay, so we do a lot of photocatalysis, and here we are focusing on water splitting and on water purification from some kind of pollutants. And further up, functional thin films. We develop functional thin films. For instance, this is the transparent coating on a glass, scratch resistance that we developed for some American partner. And this is some metallization with the help of hydrogen producing algae. And finally, we are coming to the energy storage technology. Well, you know what? I will just move to some another slides because there was a little, just give me a second. Okay, here is the same, but just prepared a little bit better for you. Okay, here we go. Yep. So, and here we are now developing, with the help of some industry, we are developing a method how to store a large amount of electric energy in a solid matter, based on one of our patents, really. Unfortunately, at the moment, I can't talk much more about that. Okay, now I think it's time to start with our topic, topological insulators. So you see, in 2016, which is just 5 years ago, the Nobel Prize was granted to 3 clever men that were working on the topological phases of matter. Now, I would like to introduce this middle guy in more details, Duncan Haldane. When you go into Wikipedia and check his biodata, you will be surprised. It has got British citizenship and Slovenian citizenship. Well, I didn't know that. I was surprised. So I went and tried to see what is the story behind that. And then I read about this, and it says like that, his mother was Slovenian born, and she met her husband, well, a Scottish guy at that time, a Scottish doctor at that time, in one of the partisan hospitals during the Second World War. So they liked each other, they married and moved to Scotland where Haldane was born. And he considers himself now as a half Scottish, half Slovenian. So it's quite normal then that we decided to work in this field. Well, it's not the only reason, but it's a more or less coincidence, but we are proud of him. Okay, so what are topological insulators? So you see, this is a typical surface of a semiconductor with a typical band structure. Band gap is there, so nothing really new, textbook stuff. Yeah, and then what are then topological insulators? Same, but on the surface, you got this sea of conductive electrons, and you got some states crossing the band gap, so-called Dirac coin with the Dirac point in the middle. Oh, so this you can imagine like a bar of chocolate. You got insulating chocolate wrapped in conductive aluminum foil. Well, just, to be illustrative. And that brings about a lot of very exotic and interesting properties. Now we must understand that these surface states here, which we call topological surface states, obviously, yeah, these are due to the bulk band structure, not due to the surface structure. So for that reason, they are very robust. Just by introducing some impurities on the surface wouldn't kill these topological surface states. So they're very robust. This is important to understand. And normally that effect comes up only for the compounds with the high Z atoms, where we can expect high spin orbit coupling and contribution. And that then would cause the inversion of states, which actually is required for this topology. Now, these electrons they have very high velocity. You can see that these topologic surface states are linearly dispersed, and they are very similar to the fermions, Dirac fermions in graphene. So for that reason, such systems would be very useful for high velocity electronics. In addition, the electrons are spin polarized, and the spin polarization depends on the direction of the propagation. So consequently, all the spintronic technology is interested in this material. So there's a lot of foreseen applications. One interesting is, for instance, spin valves, where you actually can switch magnetization without magnetic field, just by applying a polarized current, and the spin orbit torque will take care of the switching of magnetization. Now, there's just one example, but you see the physics of topological insulators is well developed and quite well understood, but there was some kind of lack of knowledge in the chemistry of these materials. For instance, we have to know in very details, first of all, you can imagine that for all these electronics, we had to contact the topological insulators with some metal electrodes. And when you contact these two materials together, you have to know what is happening on the surface, especially if you are using this surface for some kind of effects. So you have to know what is the hybridization between the electronic states of the metal and the topological insulator, and how all these topological surface states and spin polarization is influenced by this coupling, especially around the metal where the metal was deposited. So you have to know about the electronic nature of the contact. Is it Schottky or ohmic? And of course, how this behaves with the time. Is this contact stable, or will kind of change with the time? Is there any chemical interaction? Of course, all these issues are interconnected, and we have decided to look very close and in very details to this topic. Okay, now I will introduce you the most investigated topological insulator, which is bismuth selenite. This is the structure, and you see it's composed of the layers. We call them quintuple layers because each layer has got like 5 rows of atoms. So it's a covalent bonding inside the layer, but it's van der Waals interaction between the layers. So consequently, that means that it would be very easy to peel one layer from the others. So it is rhombohedral. I talked about the quintuple layers, and the other thing which is here shown on this picture is the fact that when you grow this material, they often contain a lot of structural defects, which cause some kind of conductivity in the bulk, and really then you don't have pure proper topological insulator anymore. And this is another topic. I'm not going to talk about this today, but it's another problem with these materials which still needs to be worked out. Okay, now what has been done already on the studies of the interaction of the surface of bismuth selenite with or other topological insulators with metals. Some studies have been done, but majority of them were done on just isolated metal atoms on the surface of such topological insulator. So the studies showed that if you have one atom of metal, it would just sink into the surface. It would intercalate inside of the van der Waals gap between the quintuple layers. So there would be some strain generated around this atom, and of course, this increases the free energy of the system. Okay, this is what we can understand, but there's no studies what happens above this level of the concentration of the metallic atoms. Where is this critical limit when the system cannot tolerate this extra strain anymore? So this is area where we investigate, where our investigation started. So we are growing our single crystals by ourselves using Bridgman method. Actually, we just seal metals into the quartz ampoule, melt the metals down, and then slowly cool it to obtain such ingots like here, you see. And it's fairly easy then to extract single crystal flakes out of such ingot. And now if we look the structure, the surface of such flake, so we have done this with different methods. Here we got the lead pattern. We see it's a very nice rhombohedral pattern. The stem, STM, shows also very regular surface structure. We have also done ARPES and see that the Dirac point here is at 190 milli electron volts. So, and these are now also synchrotron techniques that we are using to analyze the surface. We are using ARPES, angle resolved photoelectron spectroscopy, to understand the electronic structure, and we use XPS to understand the chemistry of the surface. The methods are surface sensitive. They give information out of few angstroms of the depth, and this is important for us because in this sense we can separate the surface events from bulk. Okay, now first we will stop at titanium. So we analyzed the titanium because titanium, it's quite often used as a first layer deposited on the surface of electronics, because it prevents then further interaction with maybe other layers that are deposited. And also in the literature, you can find a lot of cases like that, but they all report problems. So we decided to deposit titanium on the surface of bismuth selenite and analyze the interaction, if there is any. Yeah? So you see, these are now titanium spots, clusters that occur when you deposit the metal on the surface of bismuth selenite. So we analyze the morphology. That's fine. But we also then started to study the interaction of this titanium with the surface of bismuth selenite. So here is XPS of clean surface of bismuth selenite. No surprises here. The peaks are at expected binding energies for bismuth and selenium. Then we analyze the system where titanium was deposited on the top. That is different nominal coverage, and here you have 3 plots for 3 different elements. And then you see we start with the clean one, and then we increase the nominal coverage. What you can obviously see here is that the shape of the spectra of the peaks is changing very much. And this is necessarily, this necessarily means that there is some chemical interaction going on. So we were able to detect this interaction, and I would like to tell you that all this is done at room temperature. It's not any like a heat treatment or anything. The deposition of titanium was done at the room temperature, and all this analysis. So our next task is, of course, to understand what chemistry is going on here. Okay, so we deconvolute all these spectra to understand whether new species of these elements, new valence states of the elements appear, and new chemical environments around these elements. And it was no difficult task to understand that we are getting metallic bismuth. We are also getting different, here it was not so clear, but we are getting different environment on selenium, which shows that some titanium selenite appears. And if you go to titanium, we can confirm this. Even easier, we see that instead of metallic titanium, we now can assign these peaks as corresponding to titanium selenites. And that was done for low coverage, and a high coverage, high titanium coverage just confirmed all these processes. More metallic bismuth, more titanium selenite in both cases. Here we also see some metallic titanium which has not yet kind of interacted with the surface. So we are very close to write down the chemical reaction that is happening at room temperature. But we were up for more surprises because we have done the same experiment at only 130 Kelvin. And we were able to confirm that this reaction, it is solid state reaction, completely solid state, no liquid, no gases, products or reactants. This reaction also happens at 130 K, this cryogenic temperature. So that, by my knowledge, is the only reaction I have seen, solid state reaction, that would occur so low. Now, and if I write down this reaction kind of schematically overall reaction, we can see that we produce from metallic titanium, we produce metallic bismuth, and from bismuth selenite, titanium selenite. Actually, it is redox reaction when titanium gets oxidized and bismuth gets reduced. Okay, we have done more analysis. This is TM analysis, and chemical profiling over the cross-section has confirmed again a layer on the interface, a layer of titanium selenite, followed by a layer of metallic bismuth. And then we go into the bulk composition again. So that is no doubt that this interaction is significant already at very low temperatures. Now, okay, we also tried very high coverages, and I would like to show you some interesting pictures now that might entertain you. So this is pretty low coverage, 20 nanometers nominal coverage. And now then we started to increase it, and we started to see this fantastic patterns on the top of the covered, titanium covered bismuth selenide. This is real picture. These are not drawings or anything. So if you look at closer, you see how nicely they are shaped. There's wrinkles or ripples, whatever, however you call it. Yeah, and why do they appear? Actually, it's quite like in the dry apple. You know, we have quite a rigid layer of rigid substrate, bismuth selenide. On the top of it, we have a soft metallic bismuth layer, and on the top of that, we have again rigid titanium selenide layers. And when that is growing, the tension on the interfaces are becoming too much, and these ripples start appearing. It's like in the dry apple. Okay, now we are moving on. We said, okay, titanium is reacting. Let's take something more novel. Let's see what silver would do. So we deposited some silver on the top of bismuth selenide. We left it there on the shelf for a week, and then we look at this deposition again. What we have seen is that with time, in 6 days, these shapes significantly change. They shrank, and also these small spots, they just disappear, as you see. So obviously there's something is happening also with silver, and we want to see what is that. So analysis show that with time, this is EDX analysis done in the scanning electron microscope. And you can see that intensity of silver with time is dropping, like here. It does not disappear. Or also when we don't see any clusters on the surface anymore, we still see the signal of silver, which tell us that silver does not evaporate or anything like that, but actually it diffuses into the surface, into the system, into the substrate. Now, when we say diffusion, it's just a description. I don't want to prejudge what actually is happening, but this was our task, to understand what is this diffusion. Is this intercalation, or is some kind of more proper chemical interaction? So here we approach it a little bit differently. So we produce nano particles of silver and nanoparticles of bismuth selenide, and we mix it together, dry, and just left it on the shelf for a number of days. And what we have seen is slow increase of some another phase. So obviously we have seen, this is our XRD, this is XRD. So we see appearance of some new diffraction lines. To enhance this interaction, in the next experiment, we have sold bismuth selenide nanoparticles in a solution of silver nitrate with the silver ions in the solution. And this resulted in much more intensive reaction, and the peaks became even bigger, and we were able actually to identify the products. So we also went back to the powder and inspected under SCM. We have done mapping, and we've been able to see again the product, identified silver bismuth selenide, silver selenide, and we have also found some metallic bismuth particles present. So here again, all that was done at the room temperature, and we are able to write down again one redox reaction that occurs when we deposit silver on the top of bismuth selenide. In this case, we get 2 selenides, ternary and binary selenide, in addition of metallic bismuth. Certainly, silver is not good as an electric contact for topological insulator, because it will degrade with time and we will lose it. So let's go on then. What is the next one, platinum. You see, it's even more noble than silver. So here we went straight in, of course, we deposited platinum on the surface of bismuth selenite and went straight into the transmission electron microscope and inspect the cross section of this film. And what we have seen is, again, an interaction. So this white part here is a platinum, and this part here is bismuth selenite. And you can see typical layers of bismuth selenite, quintuple layers of bismuth selenite. But look at here, you have completely different periodicity of these layers in the interface here. And that means that some new compound has formed on the interface between platinum and bismuth selenite. So we still have a little bit of work to undoubtedly identify this new compound, but all the features that we have seen from the TM research show that they can be bismuth platinum selenite, or I mean you have two possibilities, but certainly some ternary bismuth platinum selenite. So also platinum, although it's not such intensive interaction, but it still interacts with bismuth selenite. And finally, then we said, let's go to our champion of the noble metals, and that is, of course, gold. Yeah? And we have repeat the exercise. We deposit gold on the surface of bismuth selenite. So you get such a clusters of gold when you start doing that, which then get denser populated, and then they even merge into such a structure that you see here. So we measure the electronic structure of this system, and what we have seen that the topological surface states are present in all cases. Of course, they're getting masked here by the presence of the gold layer. We cannot see that at some point, we cannot see that anymore, but there is no band gap opening for sure. How about interaction? So again, we have done XPS to see the interaction. XPS on gold core level, you can see that, does not change with time. So gold remain metallic for all the coverages. But when we look at the bismuth, we do see one additional component appearing here, which we call bismuth 2 here. But this is still metallic. It is not oxidized. We have seen small changes in selenium here, very small, not very obvious, and then our task, of course, to understand this happening. So what really is happening is that in this case, we do not get redox reaction anymore. Gold is too noble, but something happens, and you know what happens? Do you remember when I said that we have a lot of defects in this structure? And majority of defects are selenium vacancies. So in the system, we have an excess of bismuth, slight excess of bismuth. And this bismuth moves from the bulk into the gold layer. And we get some kind of alloy, bismuth gold alloy. So there is no interaction, just slight diffusion of bismuth into the gold layer. So we can use bismuth. Obviously, we can use we can use gold as the metal for electroding. We also wanted to see how that works at elevated temperatures. So we used our heating stage in the SCN, and we have seen that there's no reaction, but the coarsening of the film, and we would get discontinuity in the film. but obviously no interaction, no chemical interaction, even at elevated temperatures. So that's very, very good to know that we can use gold straight on the surface of bismuth selenite as an electronic contact. Now, from all these studies and from the information for also other elements, we can see that there is obvious some trend in the reaction with the bismuth selenite. And I was already talking about the redox reaction. And when we are talking about the redox reaction, then of course we can correlate the intensity of reaction, or let's say free energy change, with the reduction potential of material of the metals. And you see that this pretty much it correlates very well. While you don't get any reaction with gold, you get some ternary phases with platinum, palladium, and then you move through this mixed area into very reactive metals when you would get straight a binary phase. Now, we also wanted to understand why these reactions are also happening at such a low temperature, room temperature, and even below. And here we develop some hypotheses. I would say it's not still it's not still fully undoubtedly proven, but we believe that this is electron mediated reaction, and these electrons are coming from topological surface states. Let's take the example of titanium. So when we deposit this titanium on the top of the bismuth selenite, in between we have a sea of these topological surface state electrons. And then they can act as a kind of a channel for transporting electrons from titanium into the surface of bismuth selenite. And of course, that would trigger the redox reaction. And then we would get the reaction products at the top. But the electrons, the TSS electrons, will just move down on the new interface between these phases and waiting there for more titanium to donor electrons to the bulk. So we believe that these reactions, low temperature reactions, are TSS electron mediated reaction. The electrons work a kind of catalyst for this reaction. This is what happened, what is the reason that we get a solid state reaction at such a low temperature. Okay, ladies and gentlemen, I would like to stop my talk here. For the last slide, I would like to thank all my colleagues from the group, especially Katya. Part of this was her thesis. Sandra, there is Sandra, who's our synchrotron expert, and Mattia, who's our expert for electrical studies. We work a lot with the synchrotron and some groups in Italy, which is just across the border, 30 kilometers away. And at the end, unfortunately, I have to show this picture as well. This is the reality today. Thank you very much.
Hello, Matjaz. Thank you for a very, very, very nice talk. I knew that it would be nice as this. So I have a couple of questions to start with, just to for some clarity. So when you deposit titanium or any other metal on the surface, doesn't it go below the layers? Just always keep as islands on the surface.
As I said before, if you deposit isolated atoms, very low nominal coverage, you would get some intercalation. But our coverage was a bit higher, above this critical concentration, and we were studying the film growth for such coverages. And normally it grew like with the clusters, then eventually they merged the higher coverages.
Okay, so how does the Dirac cone evolves when you deposit? I mean, when you increase the coverage,
Yeah, it depends. It depends on the metal. As you have seen in the case of gold, you know, there was no interaction and no significant influence on the Dirac point and Dirac coin, you know, and no band gap opening. But of course, when you get some interaction, then you produce a layer of the product on the top, and you cannot then with ARPAS, you cannot analyze what is happening below at the interface of the new product and the pure bismuth selenite.
I see. Okay. And also, what is the effect of the lone pair electrons of bismuth? I mean, there is no, I don't see
now
any comment on that.
Lone pair electron, metallic bismuth hasn't got any. Is that right?
Yes.
Yeah, only when you reduce it to 3+ state.
Yes, yes.
Yeah. So I don't know. I don't know whether there is any significant effect. It might be some effect in the formation of the new product structure, you know, this steric effect of lone electron pair. But I don't. I can't.
Also, you see some new phases coming up, no?
Yes, of course. You see new phases coming up. Yeah.
Yes.
Which some of them still contain bismuth. Like in the case of silver, you get ternary silver bismuth selenite. But you see, is there any role of lone pair electron? I don't know.
Okay, thank you. So I'm waiting for any other questions. So there is one question: if there is any study on very reactive metals.
Sorry, can you repeat?
On the surface. So there is one question: is there any studies on very reactive metals on the surface?
So what metals?
So there is no specific
yeah, I mean,
suggestion.
Later on, of course, we have seen studies on iron and some other metals too. Yeah, but what we focus on the metals which are supposed to be the contact for the contacting. Yeah, which supposed not to react. Yeah, although we have seen a lot of reaction. But yes, there's a lot of chromium. You can see a lot of chromium and all the stuff done. Yeah.
Okay, so I don't see any other questions. If not, I would like to thank again for accepting our invitation and to give you such a wonderful talk. Thank you very much.
It was my pleasure.
Really honored. Thank you. Thank you.
It was my pleasure. Thank you, Praveen, for organizing this, and all of you to listening to me this 45 minutes.
Yeah, thank you.
Yeah.
Thank you.
Thank you. Bye-bye.